Hey everyone, thank you for joining me today. I'd like to talk about making Postgres the universal database. This is based on a lot of lessons I've learned trying to extend and rewrite Postgres over many years. I wanted to originally call this talk Pigby. This is based on a Silicon Valley reference, which is Postgres is great, but, it always has some room for improvement. Now a little bit about me. So I've been playing with administering, extending, rewriting Postgres since the 90s. I was a founding engineer at Enterprise DB, where I was focused on Oracle compatibility and performance. I was also CTO of MariaDB, member of the Oracle Oak Table Network, and currently I'm co-founder and CEO of Nextgress. I've shipped a lot of different wire protocols, SQL dialects, procedural languages, multiple rewrites of MVCC, auto-tuning, lots of different things on top of Postgres since 2002. Everything I'm going to discuss today has been in production somewhere, either by me, or a customer, or both. So what we're going to talk about, what you can do with extensions and what you can't, hooks specifically, proof that they work, and some of the pitfalls nobody warns you about, wire protocols, SQL dialects, and semantics, things that nobody talks about there, some differences between compiled and interpreted procedural languages, and various aspects of the core, the buffer pool, background writer, async IO, that kind of thing, and specifically MVCC without vacuum. Last, we'll end with some things that Postgres could learn from Oracle and others. I prefer to be very candid, specific, and opinionated in a lot of this. Now, my contention is that Postgres is the most extensible production database ever shipped, and one of the most architecturally constrained on purpose. Now, everything in this talk lives in between the two, and we'll get into that. So on the extension side, before I can really go to where it ends, we have to start with where it starts. And most of the people at this conference are already aware of how Postgres is at a high-level architecture standpoint. From a foundational perspective, we have all the core objects, then we have memory, and then we have the processes that are running, all the background processes, as well as Postmaster and the user processes. And we all know that SQL becomes a pipeline of fairly well-known stages, right? Parser, parse, analyze, rewrite, planning, execution. And then after execution, you get to the access manager, storage manager, and all of the things built beneath that. We don't really need to go through the specific names of things and definitions. I think everybody here knows that, but I have them here for reference. Now let's talk about hooks. Hooks are function pointers, C function pointers, that a loaded library can overwrite. The basis of it is that during loading, any extension can update those function pointers, and the core, all it does is call these function pointers. The surface of function pointers and hooks at this point is pretty big, and I believe it could be a little bit bigger. But right now, you'll see a lot of extensions that use the planner hook, process utility, and that sort of a thing. Now, hooks are great, but they do have some pitfalls. Specifically, hooks are designed to chain, and so the responsibility of the extension author is to make sure that that chain is followed. Now, there are certain extensions, like Babelfish from AWS, that will overwrite a hook and not call the chain. This is sometimes done intentionally because you don't want anything else to be called. You want to be the only one that runs it, but in that way, the load order of shared preload libraries is very important because in some cases you do want extensions to run in order, in chain order, but if you load them in the wrong order, then that won't happen. The other thing that's really important to know is that just because you set a hook doesn't mean that it'll get called in all cases. There are different cases in the core engine which will go around certain hooks, or will only call the hook if you go through one certain path. The other thing is that hooks are not fully stable, so version upgrades can move them around a little bit, and the thing is that because hooks are just used by extensions, everything's compiled, but it may not work correctly. So if you build with hooks, the key is to test every extension basically all the time, in your own test cases, in customers, stacks, all of that. Now, hooks are great again, and the community has built pretty amazing things without patching the core using these hooks. PG vectors are a really common one that's discussed these days, but I like to think of the really large extensions, and I think Citus is probably the best example of something built on hooks. It's almost an entirely different database built around Postgres using a pretty complicated set of hooks. Then we have timescale and Apache age, graph engine built into Postgres. And then there's the ones that most people know about that are more contrib-like, pgcron, pgstat statements, all of that. But the idea here is you should never modify the core if you don't have to. And so if your idea fits within hooks and the hooks exist, use them. Now let's talk about AWS Babelfish, which is an entire protocol, dialect, semantic implementation of SQL Server within Postgres with hooks. And the idea here is that AWS needed to run SQL Server Transact SQL applications against Postgres, which included the wire protocol, the SQL dialect, and semantics. And the idea was they didn't really want to fork Postgres. They tried to use hooks wherever possible, and so they added hooks where they were missing. Some of them have been accepted, others have not. I'd like to specifically talk about a couple of those in a little bit. But if your extension needs a new hook, rather than writing a lot of new code into the core, what you want to do is just write a small patch that adds that hook. If you can make a good case for it, there's a potential that the upstream will accept it, and then you don't need to maintain a separate patch anymore. Now, where the hook surface runs out, again, hooks are generally designed to add functionality, more so than replace it in Postgres, although some have done that. But what you'll see, based on the concept of hooks, is that there isn't really much for updating heap tuple formats, the visibility, transaction ID stuff. And specifically, the front-end, back-end wire protocols is one area where Babelfish added hooks to override sort of the libpq server-side component, so that you can write your own protocol handlers. And the one I think that is the most important is the grammar, because, and this is where Babelfish added this also. Right now in Postgres, you only really have the post parse analyze hook, and what you really need is, if you want to swap out the parser, like for example Nextcris does or Ivory SQL does, is you need a hook to be able to replace the raw SQL parser, and that's a hook that both has been added to Ivory SQL, as well as additionally there's not really hooks for buffer management, wall, or really changing the process model. Now, a long time ago, MySQL added pluggable storage manager, which was really awesome, and a lot of people asked, why doesn't Postgres have the same thing? So around Postgres 12, Postgres added like pluggable storage, but it's really table access managers. Now, table AMs are sort of like MySQL, but not really, and the reason is that the table AM is pretty tied to the way that heap-like storage works. It doesn't really let you change what Postgres assumes about that storage. Your storage just has to implement a very similar interface. And some gaps to that are, for example, tuple updates still only expose no update, all update, or summarizing. You can't really just update a per index update. And that's clear in a couple of cases where even in the index access manager, there is no point delete. The idea with the indexes is still that large chunks of tuples are removed from the index based on something like vacuum. Then, when you get to tuple IDs are pretty small. They work for Postgres, and they do work for some of the access managers, but there's not a lot of additional room in them. And so what happens is that if you're writing a complicated storage manager or access manager, table access manager, or one that doesn't really conform to the way that you can compress stuff into a TID, you end up having to have a layer of indirection or a sort of lookup mapping table to map TIDs to whatever your underlying structures are. This is both good and bad, but it's something that you need to think about. Additionally, the buffer pool is pretty fixed in the way that Postgres works, as well as some of the other aspects. It really assumes you're using normal heap. So really, a pluggable heap rewrite, in my opinion, is just sort of a patched heap. Now let's talk about compatibility, because this is an area that I've done a lot of work in, and some people that are doing Postgres do the same, which is that, in my opinion, wire protocols are pretty easy. Right? Writing a wire protocol implementation, for the most part, many of them are open source or standards, so you're just writing another implementation or using a library that already exists, and handling that at the server side isn't really that hard. The problem is that when it comes to how do you implement the listener of the process and all the actual protocol, is that in the old days, or in the current days of normal Postgres, what you really need is to implement your listener as a background worker. So you start up a background worker, it'll bind and listen on the port, it'll handle the incoming connections, and then either fork another backend process, and then, or connect to SPI to handle it. Or in the Babelfish case, they actually wrote those specific server-side hooks. So you can implement the server-side protocol using an actual hook-based interface, which is really nice. And I think if you look at Ivory SQL and OpenHalo, they both sort of just, integrate into the postmaster's listening process and then listen on another port, 3306 or 1521, and then handle incoming connections and just mark those as a different protocol internally. But that requires that they then put a lot of logic around to make sure that they know which one it came from. So I think this approach is cleaner. The SQL dialects to me also are pretty easy. Writing a scanner and a parser is pretty easy. The thing is that what you really want to do for the most part when you're doing that with Postgres is generate a Postgres parse tree. As close as you can get to the normal Postgres parse nodes, the better it is, because you can reuse a lot of the planning or post-parse analysis logic rather than having to rewrite your own, which makes it very simple. And then this is really where the handling of those dialects comes in. So in Transact SQL for Babelfish, or Oracle's SQL dialect for Ivory SQL, or the MySQL dialect for OpenHalo, basically those are just tracking which client connection is using that parser, and it passes through. This does create some complications when you create stored procedures, where just because of the different dialects, you need to know how to execute them, what should be handled. And in many cases, you shouldn't or can't really create, for example, a PLP2 SQL function, some of those dialects. And if you call them from a connection that uses Oracle's dialect or MySQL's dialect, for example, in many cases, it will not execute correctly because the underlying SQL parser, in many cases, is just using the current one that's set. There is a lot of logic that has to get handled to know how to set and reset that across function boundaries. But the nice thing is, right, you can write a SQL parser with lots of different tools. Doesn't really matter, but you know, a lot of times people talk about compatibility, and all it really is to them is a parser, but anybody who's just done a parser knows that that isn't really compatible, because semantics are the part that are the complicated part that most people don't actually talk about. So on the semantics side, that really means bug compatible, right? So if we think of, you know, there's a lot of different examples here, but the easiest I think that I've seen done a lot of times with tools that are designed for migration, or that, you know, blogs that people have written, is a case of like MySQL's replace. So the MySQL replace statement has what you think would be a very similar corollary on the Postgres side, which would be like insert on conflict update. But if you think that that's the same, it really isn't semantically. You would think, okay, well, replace is just, if it's there, update it. The problem is that in MySQL, that actually gets implemented as a delete and an insert, whereas Postgres doesn't. It actually gets implemented as an update. And some applications really rely on that delete and insert versus just the update. So when you think about some of these migrations and similarities, the SQL itself, you would think, is doing the same thing, but it's really not from a semantic standpoint. So that's something to be considerate of. And that's really the hard part. So in the docs, there's a lot of discussion about, you know, things that you can do to override Postgres behavior. But realistically, the complicated parts are semantic, where it comes to transactions, how they're handled, how locks are handled, how transaction isolation is done, and then, you know, even things that you would think would be kind of simple, like null handling with Oracle versus Postgres, or how types are coerced and converted, is actually very different. And then error message text also. The other thing that I like to talk about is procedural languages, and this is because it's become very common for people to say you shouldn't write stored procedures in databases anymore. They think you should do everything in the application tier. I don't believe that's true at all. I think everything should really be done, if possible, as close to the data as you can. There was a lot of research done by Oracle and others that showed that copying data out of the database to run logic actually consumes more CPU and time than it does to execute inside the database engine, which a lot of people don't think about, but there has been a lot of tests done to show that. So I think it goes back to normal computer science. Try and run your logic as close to the data as possible and minimize copies, especially with networks that are unpredictable. And in some of the cases we've seen, for example, that between interpreted procedural languages and compiled procedural languages on Postgres that we've built, that we've seen up to 43 times faster versions of compiled procedural logic than the interpreted, but the interpreted still outperforms copying data over the wire to run logic. So I just wanted to have this in there because I really believe that when people say stored procedures don't matter anymore, that is a fashionable statement, but it is uninformed. And I back this with, you know, logic running inside the database will always beat logic running behind the network round trip. I do say always. There are obviously edge cases, but for the most part, I'm going to be opinionated and say always. Now let's talk about a few other things here. So the buffer pool. Buffer pool is just one implementation. There's not really an interface, and the Postgres buffer pool is actually pretty simple. One of the things that you can actually tune, depending on your workload, is num-buffer partitions. If you have a large number of CPUs or connections, that kind of thing, one of the things you might see is that increasing the num-buffer partitions compile time parameter will actually improve performance. But the thing with the buffer pool is that, every table access manager that uses Postgres's normal table access method shares this. It is not used by foreign data wrappers, and there's no real way to slide a different policy into the Postgres buffer manager right now. It's clock sweep, and that's it. One of the things that you'll find if you're building more complex table access managers, for example, like OrioleDB, is that you have to really implement your own buffer manager, because the one that Postgres uses is really just designed for the normal heap access method. And then, I think the rest speaks for itself. The clock sweep is probably the best general purpose buffer manager, but you will see better performance with alternatives. Like 2Q has clear advantages in some cases, but you can't swap out the normal Postgres buffer manager. So if it gets complicated, you kind of have to write your own, which becomes problematic. So one background writer is not enough. I think many people who have highly loaded, databases, especially IO heavy, have run into the case where the single background writer cannot keep up. This is a patch that we did in Enterprise DB back in 2006, and I talked to very large companies just the other day who still have this problem, and multiple background writers is really necessary, and I think that depending on what happens with the patch, Postgres 19 will potentially have this as well. Now, async IO, direct IO, it's great that we finally have them. I think there's been a lot of positive feedback as that was implemented recently. But going back to the community for a long time, one of the things that has always sort of surprised me is how against this the community has been. Everybody has kind of said, just let the OS figure it out, which, given that I've done a lot of work with Oracle and other large commercial databases, we've known for 20, 30 years that async IO and direct IO are good, and it's great that Postgres has it. At Enterprise DB, when we were working on performance, we actually began doing async IO and direct IO in 2006 or so, but it really took a while for the community to catch up. It's great that they did, because this is great for anybody running Postgres. One of the complicated things that I've done in the past was build table access methods and even foreign data wrappers, or the hybrid of the two, that read Oracle data files and NODB data files. And the thing is that foreign data wrappers specifically don't participate in transactions in a very clean way. It's kind of a hacky, hook-based approach. And one of the things that I found was, especially for migrations, it was really nice to be able to just read straight from an Oracle file and format into a Postgres data file. That makes it much faster, and the complicated part is that you can't really replicate the same sort of visibility through Postgres's normal sort of snapshots. So you end up having to take Oracle's versions of transactionality and create this bridge to Postgres. And it works, but it's not very straightforward, and it does really require some core changes to make work. Now, on multi-version concurrency control, Postgres, as it was originally designed, was designed as an append-only storage system with no overwrite. The idea was that Postgres could handle even time travel queries, right? It was really amazing. It did that long before other databases, and the way it did that was to then take some of those old rows, put them on write once media, worm media, and that's what Vacuum was originally designed to do. But in Postgres 6.1.6.2, time travel was actually removed, and that was the whole reason for having the original multi-version timestamp ordered strategic approach and algorithm for MVCC and for the original Vacuum. So the problem was that we actually removed the thing that made Postgres valuable and Vacuum just became a cleanup because we just stored dead tuples everywhere. We no longer wrote them anywhere, you could no longer query them again, they just hung around in the table. So the world changed, but Postgres's architecture didn't, and this is where we have tons and tons of Vacuum-related problems today, and that's why I believe that the underlying normal heap approach and MVCC approach needs to change, because Vacuum is not a performance tuner. It's a garbage collector, and what you'll see are just tons of blogs that say how you should be tuning Vacuum. Auto Vacuum is talking about a newer version of Auto Vacuum. To me, this is all just cleaning up a mess that should be fixed at the core, which it could be, and I feel a little passionate about that, and I'll talk about why in a minute. But again, going back to Postgres' original design, transaction ID wraparound is also a consequence of the original design. It's not a bug. The idea with transaction IDs was that you could freeze, and all of the old media would be frozen. And now, though, you get a very high volume database. You're limited to really 31-bit transaction IDs, and then you have to make sure that you don't overrun that. And anybody who has a very heavily loaded database has to spend a good amount of time optimizing their vacuums to make sure that doesn't happen. Several pretty large companies that I've worked with in the past after this happened to them, went down for a while because this happened. And if you look at even the 64-bit transaction ID patch, the way that that sort of creates a multi-level transaction ID still is problematic because it's really based on a 32-bit problem, but obviously you can't just throw 64-bit transaction IDs into every row and just bloat the database. So update in place, to me, that's the correct version of MVCC. It's what every other database pretty much implements. And the idea there is that you take all your good rows, all the ones that are very likely to be read, and those are in your hot path, and you move everything else that is unlikely to be queried out of line, because then you're only having to pay an extra price to read it pretty rarely. So I do believe that Postgres should be using an update in place approach. If you look at how Oriole works, if you look at how Heap was kind of originally designed, even though that died, that's it. But it really should mimic the way that other databases have done it. And the reason I say that is in 2006 or 7 at Enterprise DB, we had two competing designs. Mine was Postgres update in place. The other one was hot. And my idea was to take update in place and do as minimal of a Postgres patch as possible by creating a shadow relation for every relation, just like we do with Toast, create an undo relation, and instead of forward chaining rows in Postgres, we would backward chain them into that undo relation. It was a little complex, and so it was sort of rejected in favor of hot, but I believe to this day that hot still has not solved the problem. And when you read every blog today, they say that your solution is to just add a bunch of free space to your database to prevent unintended bloat by intentionally bloating it. I don't think that that's a solution, but in the 2010s, probably 2014, 2015, I had this idea to create InnoGress, which was InnoDB style rollback segments in Postgres. It actually worked out really well. It was pretty clean, but I didn't end up taking it to production just because it was taking longer than expected. And then today, one of the things that we've done at Express is to take some of the OrioleDB stuff as a base and extend it with some of our experience working on Oracle and other commercial databases to be more optimal. But in each case, vacuum and wraparound go away, but a new set of trade-offs appear. And the thing is, as we know from computer science, everything's a trade-off. So when you change things, Postgres' normal heap tuple satisfies, is assumed by the executor. That's how everything is checked. The index access manager, all the extensions, but it really doesn't work because you're hiding that behind the scenes. And in that case, hot chains don't really exist in update in place either. Index only scans the new rules. And because your transactionality is hidden behind the scenes in your access manager, visibility map doesn't really matter anymore, or free space map, and logical decoding has to take a different approach. Depending on how you've done it, PG dump, base backup, replication all require some potential changes though. So yeah, nothing's free. I would say that dealing with undo from a programming perspective is harder. That multi-version timestamp ordering in every piece of literature is really the dead simplest version of MVCC you can do, because you can't really screw it up unless you screw up your visibility rules, because you just have every tuple there. So that makes it easy, whereas in undo, you're moving things around and you have to go find it and fetch it and do it in a way that's performant and doesn't create a lot of contention. So I would admit that update in place is a much harder approach, but I do think it's more valuable to the operator. And when you do that, then the DBA does have to pay attention to how does that undo implementation work and how do you still make sure that that's operational. So things that I have not rewritten just because I didn't really have a reason to. So wall is what it is. It's extensible enough being able to write a generic wall record, and there's so many downstream things that I just haven't seen a reason to rewrite it as is. The system catalogs are kind of a pain to deal with from a bootstrapping perspective, but everything depends on them sort of behaving as they do. So it's easy to leave that alone. I think me and a lot of other Postgres internal people have at one time or another played with a multi-threaded version of Postgres. I have one that works just like others do. The problem is really the ecosystem. I can't think of really any good extension or large extension, popular extension, that doesn't expect Postgres to work in a process per connection model. And I think going to multi-threading, while it could be valuable, creates a lot of complication for the ecosystem. And I mean, honestly, multi-process is pretty much fine as long as you're using connection pooling. There are some optimizations you could do with connection pooling as well, but we're not talking about it in this talk. And then, Postgres wire protocol is what it is. I think there's room for improvement. It's pretty simple, and I think more could be optimized with some negotiation, but almost everybody who builds a Postgres compatible database uses that protocol, so it's easy to just leave it as is. What could Postgres learn from other systems? I think from Oracle, it's A lot of people used to claim Oracle's undo was a problem because of snapshot, or, basically your old data not being in the rollback segment anymore. But it really is a design. It's not a compromise to be date and place and to use undo. That's what OrioleDB is doing, and it's the right approach. InnoDB, I think clustered primary indexes, Oracle has these with IoTs. Most databases have index organized tables of some kind. Postgres has the cluster command, but not a lot of people use it. It's a pain to keep things clustered, and I think doing that as a primary key is very often valuable. SQL Server, for example, has columnar built into the same engine. It's not a bolt-on thing. MongoDB documents as a first-class object. I think JSONB has worked really well for Postgres in that case. So not a lot to do there. I think there's some improvements for JSONB, but I do think that for small to mid-size, like Mongo databases, Postgres is just as good, if not better. And MySQL, though, I would say that almost everybody that works with Postgres knows it's kind of a pain to set things up, to administer, especially things like a replication. It's really hard. And one of the things that Monty really did well with MySQL was with his 15-minute rule, that if you couldn't download the database and get it running and do, set up something pretty easily, then as engineers they had done something wrong. And I think, if you look at how easy it is to set up many things on MySQL, that is still true today. Postgres is not like that. And I think that's a good rule to follow, something we could learn from. I do think, though, what many of those could learn from Postgres is the extension ecosystem. Some of the databases have ways to extend them, some easier than others, but I think nothing really replaces what has been done in Postgres' extension ecosystem. And it's so many different people solving lots of different problems. Sometimes there's 5 different solutions, some are better than others, that kind of thing. And that has its own set of challenges, but I think that it's a very collaborative world that Postgres has, where people are just and they're just designing to solve problems, and there's a lot of solutions out there. And even if the perfect one that you're looking for isn't there, there's very often something to start with. So I think a lot of them could have learned from Postgres there. So in general, don't be afraid to rewrite, but be afraid of not learning what the core was trying to protect. Thank you.